So you have to share screen.
Yeah. The middle, no, not the middle one.
And tab.
Maybe we'll try this one. Yeah, we had this problem.
Okay, so we pull it out. Let me, we'll just pull it out as a separate window, and now we can share.
Yeah, I wasn't seeing it as a C.
There
There it is. Okay, great. It is recording, so yeah.
All right.
So I will introduce you.
All right.
The next speaker is Mutasim, and he will talk about triangle families with large edge of Laplacian spectral gap.
All right. Hi, everyone. So I want to talk about this spectral parameter about of certain graphs, or rather triangle families. You can either approach it from either perspectives. I first learned about, the parameter itself I'll define today, but the parameters come as the bottom part of the spectrum of certain matrices, which I learned about 4 years ago. That was my first PhD project when I was at Delaware. So I'll give you a little bit overview after I define the topic as to why I think it's an interesting thing to study. And I'll keep the proofs and whatnot very short. I'll just give you a brief overview of how the proofs go, but I'll not do any full proofs at all today. Okay, so let me first define the object. Bear with me for a few slides. So I'm going to define it for an arbitrary set of 3 sets. So 3 element subsets of some, think about some arbitrary set which is totally ordered. And given such a family, non-empty finite family, we can create the support graph, which I'll denote by gamma sub 0. And it is basically the minimal graph that would support these 3 sets as triangles. So you take the union of these 3 sets as your vertex set of the graph, and take pairs of the ground set elements that appear as subsets of these triangles. This is what I'll be calling the support graph. And given a support graph, we can define the triangle boundary matrix, which I'll denote by this partial 2. Here, partial is for the boundary, and 2 is because we're dealing with the triangles. If you do the similar thing for edge versus vertices, you get the signed incidence matrix that Sebi introduced an hour ago or so. So this is the triangle level analog of that matrix. So this is a matrix whose rows and columns are indexed by the edges and the triangles in the graph. Note that I'm not taking all the triangles in the graph. Rather, I'm restricting myself to a particular subset of the triangles that is available. So the entry at E comma T in this matrix is going to be either 0, 1, or -1. It's going to be 0 if the edge is not contained in the triangle, and it's going to be -1 if the edge is like the middle edge. You have a total order on the vertex set that induces an order on pairs in an obvious way. And if the edge is the middle one in that triangle, you put a -1 sign. And if the edge is either the smallest or the biggest one, you put a sign +1. I'll tell you a little bit more about like why this sign convention was adopted, but for now, bear with me. And we define the triangle down Laplacian to be this matrix transpose times itself. Now, if I do it the other way, partial 2 times partial 2 transpose, that is similar to the signed adjacency matrix times itself, as you saw a bit earlier, which happens to be the usual graph Laplacian of the usual graph Laplacian matrix. Here, I switched the order because of 2 things. First of all, the non-zero spectrum of these 2 matrices, even if I switch the order of the multiplication, is not going to change. That's a basic theorem in linear algebra. But dealing with triangles is easier, in my opinion, for this work. Also, if I'm dealing with arbitrary sets of triangles, this definition is easier to work with, because otherwise I'll have to think about vertices and edges that may be in my graph that may not be in the triangles, etc. So I'm going with the triangle definition, but of course you can work with the matrix that you get by partial 2 times partial 2 transpose, and basically you'll derive the same theory. Okay, so here's a quick example before I go any further. So I'm starting with a very basic example with 2 triangles at the bottom, at the top. So 1, 2, 3, and 2, 3, 4. I'm ordering them in the natural way. 1 is less than 2 is less than whatever. And then the matrix, this is the partial 2 matrix, the boundary matrix. It has 2 columns indexed by the matrices 1, 2, 3, and 2, 3, 4. And the rows are indexed by all the edges that appear in this graph. And as you can see, the signs are what they should be. It's 0 whenever the edge is not contained in the triangle, and 1 or minus 1 depending on the sign convention. And we get the corresponding triangle down Laplacian is what I'm calling it. So if you've studied algebraic topology, you'll realize that all I'm doing here is that I'm writing down the matrix form of the 2-dimensional simple shell complex, whose one skeleton is the graph, and the 2 skeleton is the selected triangles. So this is nothing new. We didn't invent it. It's just standard machinery from algebraic topology. But what we're going to do now is that we're going to move away from the homology or whatever study to the spectral study of these matrices. Okay, so as you can guess, it's not possible to directly study the eigenvalues of the partial 2 because it's not a square matrix. So we create the gram matrix and study that. So okay, I'll go there in a second. Let me explain why this is something one would want to study. So as Sebi was describing earlier, I'm going to piggyback on his talk a few more times. So sorry about that. So the Laplacian eigenvalues of a matrix sometimes tell you a lot of important things about the graph. In particular, it tells you about the number of connected components, and the second smallest Laplacian eigenvalue tells you about how well connected the graph is. So there's this very well-studied family of graphs called the strongly regular graphs family, which are more than regular. So every pair of vertices have the same number of common neighbors, and every pair of non-adjacent vertices have the same number of common neighbors, etc. But the problem is that you cannot distinguish strongly regular graphs that have the same parameters, these numbers that I just described, using the adjacency or the Laplacian eigenvalues. You need something else. So in our first paper in this line, we with Sebi, Crystal Gu, and Shunzi Ji, we looked at various families of strongly regular graphs where they have the same parameters, so the same adjacency and the spectral adjacency and the Laplacian eigenvalues, but they were non-isomorphic. And for most of them, not all of them, for most of them, it turned out that if we looked at the eigenvalues of this matrix that I just defined, these eigenvalues are strong enough to distinguish all those families. So I'm not going to go into all the details. I'm just going to give you this one example family, which was, I think I have it listed here. So there was this big family of 3,854 strong regular graphs, all with the same parameters. And they all had different spectrum in terms of this matrix that I just defined. So clearly, these matrix eigenvalues are detecting something in the graph. Sometimes it is strictly stronger than what your adjacency or the Laplacian eigenvalues can. But okay, so there's that. But unfortunately, these eigenvalues have not been studied to the extent at the level that the usual graph and Laplacian and the adjacency eigenvalues have been. So later in our second paper that we're working on, we also looked at the multiplicity of the zero eigenvalue for these matrices. And it turns out that for almost all strongly regular graphs, whatever almost all means here. I'm not going to go into that. It turns out that the zero multiplicity of the zero eigenvalue can be read off from the graph parameters. And so there's clearly something to study in terms of the graph structure versus these eigenvalues, which have not been done, at least not to the extent I would like to understand these things. So that study is what my talk today is about. So in particular, I'm not going to talk about the entire spectrum. I'm going to focus on the bottom part of the spectrum, which is the smallest non-zero eigenvalue, which will be the smallest positive eigenvalue of these matrices. And this is the exact edge level analog for the algebraic connectivity, the second smallest eigenvalue of the usual Laplacian. So this is the edge level analog of that classical algebraic connectivity of the graph. And I want to understand if this says anything. In particular, like how big can it be given a certain number of edges and vertices in your graph, and what sort of graph structure forces this value to be large. But there's a small problem, is that if your triangles do not see certain vertices and edges, they are not encoded in the spectrum of this matrix. So what you want to do is you really want to study these eigenvalues in terms of the triangle family that you're selecting and the support graph that is created by those triangles. Any vertices and edges, even if they do form triangles in the graph, but are not contained in this triangle family that you've selected, their data will not get encoded in the eigenvalue. So there is no loss in the spectral data if we just study this entire subject from a perspective of arbitrary set of three elements sets and not by starting with a graph. Okay, so with those simplification in place, I will define this lambda of t to be the smallest positive eigenvalue which always exists. Yes. Oh, it's the fancy name for the second smallest eigenvalue of the Laplacian matrix of a graph.
Can I ask you an elementary question?
Sure.
So the matrix, you're looking at matrices where you have edges on the columns and triangles on the triangles on the columns and edges on the rows.
So this was the original matrix boundary. Now I'm taking that transpose times that. So the rows and columns would be indexed by triangles.
Okay.
Yes. And in fact, you can check that on the diagonal, you're always going to have threes, because there are three edges in a triangle, and the off-diagonal entries are going to be 0, 1, or -1. And you can write down an exact nice formula for what those coordinates will be, but that's not what I don't want to do that now because we don't need that. Okay. Smallest positive eigenvalue, because there might be more than one zeros. Yeah. Okay. So for arbitrary finite non-empty set of three elements sets, I will define lambda of t to be the smallest positive eigenvalue of the triangle down matrix I just constructed. And one can check that the arbitrary but fixed order we chose to be on the ground set is irrelevant. If you choose a different order on the ground set, it's just going to conjugate the triangle down matrix with an orthogonal matrix. So it's a similar matrix. The eigenvalues will not change. Lambda will not change. So the order is irrelevant. This is really just a honest-to-God parameter of the triangle family. Okay? All right. So what sort of structures can we expect if in the graph or in the triangle family if I know at least the bottom part of the spectrum? But before we go there, I want to define these two extremal functions. Is that, first of all, as I said, your graph may have extra vertices and edges, so it's not a good idea to try to optimize lambda based on the number of vertices or edges, but you can ask a question about how big your lambda can be if you have a fixed number of triangles in your family T. And I'll define two versions of it. Small phi to be small phi of t to be the largest lambda you can achieve out of a triangle family of exactly size t, and uppercase lambda of t to be the maximum lambda you can get out of a triangle family of size at most t. Okay, so it'll turn out that the second one is easy to calculate. There's nothing, not much interesting things to study there, but the first one, phi of t, is the more interesting one. Anyway, so these are the sort of questions I want to ask, but if you don't want to read all of those, really I want to understand how big, if your lambda is big, the bottom part of the eigenvalue is bounded away from 0, what sort of structure does it force into your graph? I'm hoping for something that kind of looks like the connectivity results for the algebraic connectivity. And really, what is the growth rate for the phi and lambda? How fast can it grow? And the third question is like, what kind of triangle configurations result in big lambda? Those are the really three questions I want to ask. Yes.
So your complexes, like you don't care, like if you have like tails or something.
Exactly, because the tails do not get read by this matrix anyway. So I'm getting rid of the
It's only doing like
triangle versus triangle. Yes, it's all about how the triangles overlap with each other on edges, not even on vertices. Okay, so first result is that if you're I'm going to call the lambda of a fixed triangle family to be just lambda instead of lambda of t. It turns out that you can do a standard Riley quotient trick with the indicator vector of a vertex of an edge to prove that the support graph will have at least n vertices, where n is the ceiling of the lambda of the triangle family, and the minimum degree, that's the important one, is at least n minus 1. So the minimum degree in the support graph is at least the ceiling of the lambda of the triangle family minus 1, and every edge is contained in at least ceiling of lambda minus 2 triangles. So in particular, if you're the first corollary, if you have some graph and you choose some triangle family in that graph, and that triangle family produces a large lambda, the smallest positive eigenvalue, that means the graph has a dense subgraph somewhere. In fact, it's a support graph of those triangles. And it immediately gives you this nice counting lemma that will be important in a second, that gives you a relation between the number of vertices, edges, and triangles versus the how big your lambda is. And once you have this, you can essentially immediately answer how big the uppercase lambda can get. So basically, you can see that if your triangle family has size less than n choose 3, you can just plug in these values and then see which one gives you the highest value. You can immediately get that for triangle families of size less than n choose 3, your lambda, the bottom part of the eigenvalue, cannot be more than n minus 1. In fact, at the size n choose 3, if you want to have lambda to be bigger than n minus 1, the only configuration that achieves it is the full triangle family of a complete graph, and in that case, lambda will be n. So so basically, that's the first structural result. Like if you're, I'm calling it a rigidity result, but basically, it gives us an idea as to how big the lambda can be. And so basically, the uppercase lambda, the highest lambda you can get for various triangle family sizes, is a step function, which is not surprising. Of course, it's going to be a step function. But what is interesting is that the jumps happen at these n choose 3 points. And even though these are eigenvalues, the ceilings are always integers. So these are not some arbitrary decimal numbers. So that was interesting to me, because even though we're computing eigenvalues of arbitrary matrices, anyway, so that basically tells us how the uppercase lambda looks like. There's nothing interesting there. Also it grows at the cubic root rate of t, the input size. Okay, so the more interesting one is the phi, which is a exact triangle family size versus how big can you grow. So I'll mention 3 results without really going into how I prove them. So first of all, phi is non-monotone. As soon as you achieve the value n at n choose 3, immediately after that, your value goes down. So there is no way you could, for example, like organize 10 choose 3 triangles, 10 choose 3 plus 1 triangles to get a lambda bigger than 10 or bigger than 9 even. In fact, you basically have to traverse the entire, a positive proportion of the entire, interval between n choose 3 and n plus 1 choose 3 before you can recover back to above n minus 1. So phi is very non-monotone. Regardless, the growth rate of phi is the same as the growth rate of uppercase lambda, which is in the cubic root of the input size. So the upper bound we already have from the lambda, because lambda is at least as big as phi, and that's bounded above by t to the 1/3. How do we get the lower bound? This is the last topic I want to talk about. So to get the lower bound, we have to do some construction. So I'm going to define this graph G sub here, G sub CB, to be a graph that has a complete graph on C vertices at the core, and B isolated vertices are joined to every vertex in that core. And using elementary linear algebra, you can prove that the spectrum of, I also take T to be the complete triangle family in this graph. And you can prove that the spectrum of the triangle down matrix that you get out of this triangle family has exactly 3 eigenvalues, 0, C, and B. Assuming B is not equal to 1, then because then you get another big clique. And so basically, it gives you a triangle family whose lambda is about 1/3 at the bottom. But how do you do it for arbitrary numbers? So you need a small number theory lemma that you can prove by modifying the Frobenius coin problems proof a little bit. But it does require a little bit of work. But you can prove that if you fix any positive integer a, at least 3, then all sufficiently large integers n, it's about 2a cubed, can be written in this form. So you see there are 3 terms here, and each term is counting the total number of triangles in the graphs that I just described. And the core sizes are a choose 3, a plus 1 choose 3, and a plus 2 choose 3. So if I create a triangle family by taking disjoint copies of G sub CB that I just described, their lambda for that family would be at least A, and the size would be whatever suitable size I'm looking for. So basically, immediately from here, by taking disjoint copies of that G graph I defined, you get a lower bound on phi. So that gives you the lower bound. So that's basically all the results I wanted to show. I'll just end with what is not understood. Basically, what is not understood is even though we understand how fast phi grows, we don't really understand what structures achieves the best lambda. Of course, for the clique threshold values like n choose 3, we know there's the unique construction, the complete graphs triangle set, that achieves the highest value, but away from it, it's not very clear what is happening. In fact, outside of some brute force computation, I don't even know exact values of phi for anything beyond 10. And obviously the h that I defined as to once you dip from the level n at the clique threshold, right after the clique threshold, how long does it take you to get back? We know that it's in the same order as the entire length of the interval, but exactly how much we don't know. So these are the 2 problems I'd like to solve. So yeah, that's basically it. Thank you.
I have a quick question.
Mhm.
So you between the same triangles with edges,
Mhm.
what about the lower problem, like you edges, vertices, and if you have a bunch of edges?
But that's just your Laplacian.
Yes, I understand.
Uh-huh.
It's not my Laplacian, but
Uh-huh.
what is the like? What is the problem there? Like,
No problem. You can do exactly the trick I did with the Riley quotient test, and you get similar expressions. So I think what you'll get is that if your algebraic connectivity, by algebraic connectivity, I mean discard all the zeros, start with the smallest positive one, and then you'll get a similar expression based on every edge, every vertex will be contained with many edges.
how does the problem translate in terms of graph theory? It's something like the form that I have a bunch of edges. How do I put them such that I maximize algebraic connectivity, or is it something? Like
It's
that?
something like that. Yes, exactly.
Important for you to, that's easier for people to grasp than
Uh-huh.
triangles and
Yeah. But yeah, what he says, yeah, that's exactly the edge versus vertex version. Yes.
Thank the speaker again.
All right.
We'll start in 3 minutes. And it's going to be a board talk. So
I'm sorry.
turn on the video and
Okay. We need to. Okay. I'll turn it on for you.
thank you.
I have to go to a meeting.
Is there a way to pull this up?
Oh, I think there's a. Yeah. So I will do that later.
Okay.
Unclear.